Okay, so what we're talking about today is called stoichiometry. Um, it's kind of a combination of stuff that we've already talked about before, and it's how we're going to calculate how much product should be made from any given reaction, or how many grams of reactants we need in order to not waste anything. All right, so just real quick, a little bit of vocab review. The first thing is reactants. So those are the substances in a reaction that are there when it starts. Um, and they're always going to be written on the left side of the equation. You've got your products, which are whatever is made by the reaction. This is what you end up with at the end of it, and those are always going to be over on the right side of the equation. And then, like we talked about the other day, you've got subscripts, which are the small numbers inside the chemical formulas, and they tell you how many atoms of each element there are. And then coefficients, which are the large numbers that go in front of the formula. That tells you how many molecules of that substance you have in the reaction. All right, so all that should be a review from last week, but I just wanted to put them in there again just in case. Okay, remember we talked about this last week as well, balancing equations. The first step in any of these stoichiometry problems that we're doing is going to be making sure that your equation is balanced, because if it's not, then your answers are going to be way off. All right, so in order to balance equations, remember you've got to obey the law of conservation of mass, which basically just means that you have to have the same number of atoms on either side of the arrow. And then when you're balancing it, the only thing that you're allowed to change is the coefficients. So you can't touch the subscripts at all. It's only got to be the coefficients. So if we look down here, we've got our CH4, which has the one carbon in the middle and then 4 hydrogens around it. And then in this is a balanced version, it's got 2 O2 molecules. It's a total of 4 oxygen atoms. Over on the right side, we've got CO2, so there's our 1 carbon and 1 carbon over here. And then if we count the oxygens, we have a total of 1, 2, 3, 4. 2 from the CO2s and 2 from these two H2O molecules. And then last thing, if we count our hydrogens, we've got 1, 2, 3, 4 of them as well. So in order to balance this, we put a 2 in front of the O2 and a 2 in front of the H2O to make everything match up. All right, so that's review again. We've done this equation actually multiple times, balancing it and using it as an example. So hopefully it's one that y'all are pretty familiar with by now. All right, and so how that's going to come into play today for stoichiometry and doing stoichiometric calculations is that we can use those coefficients to figure out the ratio of moles the ratio of moles between whatever two compounds we want to. So once this equation is balanced, if you look at these coefficients, they'll tell you how many moles there are of each one compared to the others. So in this reaction above, the same combustion of methane reaction, for every 1 mole of CH4, there are 2 moles of H2O. So because the coefficient in front of CH4 is a 1, if it's not there, it's assumed to be a 1, and because the coefficient in front of the H2O is a 2, that means that the ratio between them is 1 mole of CH4 for every 2 moles of H2O. Right? For every 2 moles of O2, there is 1 mole of CO2. So because the coefficient here is a 2 and the one here is a 1, that means the ratio between them is 2 moles of O2 for every 1 mole of CO2. So to find the mole ratios, all you're doing is looking at your coefficients. Okay, so once we know that, we can use that along with our knowledge of how to convert between mass and moles to find the mass of any of these compounds in there, given that we know just one of them. Right? So the way that's going to work is you'll be given the equation. Usually I'll make you balance it, but since we've used this reaction a bunch of times, I'm just giving you the balanced version. And then the question will be something like this here, where it asks if you have 10 grams of CH4 that are consumed in the reaction above, how many grams of H2O will be produced? All right, so it tells you the mass of the CH4 here, and it wants to know what the mass of the H2O will be at the end. So the way we're going to do this is by starting off by converting from mass to moles of our CH4. All right, so let me switch this over to the right view for y'all. There we go. So if we know we have 10 grams of CH4, what we need to know, our first step is converting that to moles. So we're going from mass to moles. So to convert from mass to moles, we need to know the molar mass of this compound. So we're going to take our carbon and our hydrogen and find the atomic mass of each one of them. For the carbon, that's 12. And for the hydrogen, it's 1. And then we multiply each of these by the number of atoms in the formula. So here in the CH4, there's 1 carbon and 4 hydrogens. And then add them together to find the total molar mass, which ends up being, 16 grams per mole. All right, and hopefully this is just a review for y'all. I threw in the review of this process yesterday. That way y'all could kind of refresh yourselves on it. So once we know our molar mass here, we're going to use that to figure out how many moles of CH4 we have. All right, so to do that, we're going to take the mass that we were given in the problem, our 10 grams, and divide it by the molar mass that we just found. So 10 divided by 16. And that, I don't know off the top of my head. So let me pull up a calculator real quick. All right, so 10 divided by 16 comes out as 0.625 moles. Okay, so we've taken the mass that we were given, we've converted it to moles of CH4, and then this next step is the one that you guys haven't seen before. This is the new thing that we're throwing in there today. This is using the mole ratio in order to convert from moles of CH4 to moles of whatever it's asking about, in this case, H2O. So we're going to look at our equation, and if we go back and look at it here, our coefficients are 1 in front of the CH4 and 2 in front of the H2O. So that means our mole ratio is 1 to 2. All right, and what we can do with that is set up a proportion. We can say we have 1 mole of CH4 over 2 moles of H2O, and that's going to be equal to this number we just found, our 0.625 moles of CH4 over some unknown number of moles of H2O. And once you've got it set up correctly like that, it's just cross multiplying to solve it, or butterfly method, or whatever your math teacher calls it. But you're going to multiply the two that are diagonal from each other. So in this case, 1 times x just comes out as x, and 2 times 0.625 ends up as 1.25. Is that right? Yeah. Okay, we don't have to do anything else because we already have it solved for x here. So that's 1.25 moles of H2O. Alright, so that's the step that we haven't seen before. So if you get hung up on anything, it'll probably be this step, but just let me know if you get stuck on it and I can come around and help you out, or, shoot me an email. So we've gone from mass of CH4 to moles of CH4 to moles of H2O. It's 1.25. And then your last step, what it's asking for in the question, was grams of H2O. So your last step is going to be going from moles to grams. But again, you guys have done that before. All you've got to do is find the molar mass of H2O and then multiply the number of moles you have by that molar mass. So if we're looking at H2O, we've got hydrogen and oxygen to worry about. Hydrogens weigh 1 and oxygens weigh 16. Then we have 2 hydrogens and 1 oxygen for a total of 18 grams per mole. And then we're just going to take that and multiply it by the number of moles we have. So 18 times 1.25 gives you 22.5 grams of H2O. And that will be your final answer because that's what the question was asking you for. Okay, so really this step here in the middle is the only new thing, but putting it all together can end up being a little bit tricky. This is probably the unit that students have the most trouble with throughout the year. So, don't be afraid to ask questions if you do get stuck on anything. All right, we're going to do one more problem together. So let's look here. This one, I didn't balance this one for you, and the ones on your homework will be more like this, where you've got to balance them as well. But what we're looking at here is that we have iron plus oxygen yields Fe2O3. So your first step in this is going to be balancing that equation, right? So let's go look back at the paper here. So first thing we want to look at here is probably our oxygens. Will save us some time. If we have 3 oxygens on the right side and 2 oxygens on the left side, there's no number that we can put in front of here that will make it match 3, right? It would have to be 1.5, and we can't have that decimal place in our coefficients. So like we've done previously, when you've got these even and odd numbers that don't match up, you're going to multiply the whole odd side by 2. So put a 2 as our coefficient here. And that gives you a total of 2 times 3 is 6 oxygens. So in order to match that up, we've got to put the 3 right there. And then our last step is balancing out these irons. So there's a total of 4 irons on the left from this 2 times 2. So the coefficient over here would have to be 4 as well. All right. So that's our equation balanced. And the question was asking how many grams of O2 are needed to react completely with 42.7 grams of iron. So we're looking at our starting point here is 42.7 grams of Fe, and we want to know how many grams of O2 that will make. So just like in the previous one, our first step is to try and convert from mass of Fe to moles. So let's look here. We got to go find on the periodic table the atomic mass of iron. So let's bring that up for y'all. And we're looking right. Oh, I lost it. Right here. Sorry. At iron, its atomic mass is 56. So that's what we're going to use. And, it's just this element by itself. We don't have to worry about anything else fancy going on. So we're going to say the 42.7 grams divided by 56. And that will tell us how many moles of iron we have. So that comes out as 0.7625 moles of Fe. Okay. So we've gone from mass of, let's do that up here again. Mass of iron was 42.7. We converted that to the moles of iron. Okay, our next step is to convert that to the moles of O2, because that's what we're looking for as our answer, is O2. All right, and so this is the step where we use the ratio. So if we're looking here in our balanced equation at the coefficients, we have a 4 in front of the Fe, so we can say we have 4 moles Fe over 3 moles O2, because we have this 3 here as a coefficient for O2. And we're going to put that equal to 0.7625 moles that we just found of Fe over some unknown number of moles of O2. Okay, so to solve for x here, we've got to cross multiply. So the two on diagonal from each other are 4 and x. And the other diagonal is 3 times 0.7625, which comes out as 2.2875. And then to get x by itself here, we need to cancel that 4 out. So we divide both sides by 4. And we end up with x is equal to, and then this decimal just keeps getting longer, so at this point I'm going to round it off and call it 0.57 moles of O2. All right, and then our last step, because remember our question was asking us how many grams of O2 we need. So our last step is to convert to the mass of O2. So in order to do that, we need to know the molar mass. So we got oxygen, it weighs 16, and there are 2 of them in that molecule. That's a total of 32 grams per mole. And then we're going to multiply the number of moles times the molar mass. So 0.57 times 32 gives us 18.24 grams, and that is our final answer. All right, so that's the process that you guys are going to be working on. This one is a little less kind of creative thinking focused than balancing equations. Once you have the equation balanced, it's kind of, these are the steps you have to follow, but it is easy to get tripped up and to make a mistake somewhere, so be careful, and if you get stuck, let me know and I will help you guys out. All right.